Hello guys, welcome back to chemistry and organic chemistry exams prep. This is Dr. Kulbhushan. So today we are going to tell the short story of organometallic reagents. So far we have covered the Gilman reagents, Grignard reagents and other organolithium reagents in great details in previous videos. However, I would like to present a summary of these to you so you can quickly review all the organometallic reagents in few minutes. So today we are going to compare and contrast amongst these organolithium compounds, namely the Grignard reagents, organolithium reagents and Gilman reagents. So Grignard reagents general formula is RMgX. One example would be methyl magnesium bromide. They are known as alkyl magnesium halides. So the carbon metal bond here is very polar, and that is true for other alkyl lithium compounds as well alkyl copper compounds. So the second type here is the organolithium compounds. Those are alkyl lithium compounds. One example would be methyl lithium. And the Gilman's reagent, the general formula is R2CuLi, that is alkyl group here is in this example methyl, so dimethyl copper lithium here. Now these are known as lithium dialkyl cuprates. R group here for all of these could be an alkyl group, just like the methyl shown here. It could also be alkenyl group, which is the carbon that the magnesium is connected to is an sp2 carbon. So and they are also known as vinyl groups. And the third type of R group could be alkynyl group, which is the carbon that is magnesium connected with is an sp carbon. The last type or fourth type of alkyl groups here is the aryl group. So aryl group is like phenyl group, or it could also be some other organic aromatic compounds. And so now let's see the X type. X is the alkyl halide here. Usually we have chloride or bromides. Those are most effective. Sometimes we also see the iodides of the Grignard reagents. For the Gilman's reagent, you can make the Gilman's reagents with the same alkyl group, alkenyl group, or alkenyl group, or aryl group. Now, if we see their nature, we know that the carbon metal bond is very polar. All of these organometallic compounds, because the metals are more electropositive, so they could be thought of as having a partial positive charge and carbon a partial negative charge. And that is the reason that all of these organometallic compounds are nucleophilic in nature. So all are nucleophiles, but now as we see here, there are some differences between the nucleophiles here. The Grignard reagents are called hard nucleophiles. Hard means here more reactive, or it means more stable. Now the other type of nucleophile that we see here is the soft nucleophile. Now the discussion of hard nucleophile versus soft nucleophile is for some other time, because it's the topic of higher level chemistry. I would say it's beyond undergraduate level, but one can understand that the hard nucleophiles would react with the carbonyl groups and the soft nucleophile would not react with the carbonyl group. So if you want to have a look on their nature, hard versus soft nucleophiles, so one also need to see the hard versus soft bases, and molecular orbital theory. So I'm sure we will discuss that some other day, but let's continue our discussion here. The reactions of organometallic compounds. So these all of these organometallic compounds would give three types of reactions. First are nucleophilic addition reactions, then nucleophilic substitution reactions, and third is acid-base reaction. So these are true for all of these three types. Now, Grignard reagents and organolithium reagents, they are similar. So they would behave pretty much same way. Gilman reagents are different. They would react differently. There are some reactions that are common of Grignard as well as Gilman reagents, but generally the organolithium compounds, organolithium reagents would give the same reactions that of the Grignard reagents. So the first reaction we are seeing are nucleophilic addition on carbonyl groups. So the Grignard reagents would add on a carbonyl group. We have seen these reactions before. They are two-step reaction. So the first step is that the nucleophile would approach the electrophilic carbonyl carbon, and once you form the tetrahedral intermediate, the second step kicks in and you would use the acidic workup. So after acidic workup, what you get is the carbonyl group gets converted to an alcohol group, and the carbonyl group is now connected with the carbon that came from the Grignard reagent. So this is the methyl group that is here. So we have increased in this way the carbons, number of carbons. So it's an important method to increase the carbons in a compound. Now, if we see the Gilman's reagent, so Gilman's reagent would not directly add on to the carbonyl group. Instead, because they are soft nucleophiles, they would instead attach at the 1,4 position. So if you consider this as 1, 2, 3, 4, so the Gilmans would not attack the carbonyl number 2 carbon. Instead, they would approach this number 4 carbon. So the conjugate addition takes place in case of Gilman's reagents. And in this reaction, overall, you would have to do the acidic workup after 2 steps. The carbonyl group remains unchanged, and as you see here, we have increased the carbon chain. So this 1 carbon came from this lithium dimethyl cuprate, the Gilman's reagent. So that's the major difference here, that the carbonyl groups would undergo nucleophilic addition with Grignard reagents to give primary, secondary, and tertiary alcohols. However, the Gilman's reagent would do 1,4 addition on carbonyls, and in this way you increase the carbon chain, but you would not change the carbonyl group. So the carbonyl group remains unchanged in this, as we see here in our current product. Now, the similar way, the nucleophilic addition reaction of Grignard reagents with acid chlorides or esters, if this Cl were to be OMe group, for example, O-methyl, that's called the methoxy group, and so the compound becomes an ester. So the carboxylic esters are made of carboxylic acids and alcohols, and the functional group is RCOOR. That's your esters. So if you were to have acyl halides or esters, the Grignard reagents would add on them twice. So you need 2 equivalents of Grignard reagents, and the product is an alcohol. You may see here that methyl magnesium bromide, we are adding these 2 methyls because of the methyl that is coming from the Grignard reagent. Now, if we see the similar reaction with Gilman's reagent, the Gilman reagent would not add on the carbonyl as we just saw earlier. So in this case, however, it will substitute on a carbonyl carbon. So once that substitution occurs, it's again two-step reaction. So first step is formation of a tetrahedral intermediate, and the second step is the good leaving group leaves. So this is our intermediate, that's our leaving group, and we got the methyl group from Gilman here. So once the tetrahedral intermediate collapses, you form the pi bond again and the leaving group leaves. So that's your product. So as we see here, it's a ketone. So the Gilman's reagent can be effectively used to form ketones out of acid halides and esters. As we see here, they would not directly attack the carbonyl carbon, and one can utilize that to the benefit of organic synthesis. Since they won't react with the carbonyl, so the Gilman's reagent won't react with carbon dioxide, which has a carbonyl group. However, the Grignard reagents, they will effectively react with carbon dioxide in again two steps to form corresponding carboxylic acid. So here we have a phenyl magnesium bromide, and we add that phenyl magnesium bromide by nucleophilic addition to the carbonyl group, and after acidic workup we get the benzoic acid, the product. Now, the Grignard reagents, they would not directly react with alkyl halides by substitution reactions. However, the Gilman's reagent, they do react with the alkyl halides by substitution nucleophilic second order. And once they do, they produce hydrocarbons. So one example here we are seeing is the bromide here, alkyl bromide. So 3 carbons. So it's meth prop. So it's propyl bromide. And once you react the propyl bromide with lithium dimethyl cuprate, it gives you a 4 carbon compound. So 1, 2, 3, 4. So out of 3 carbons, now the product has 4 carbons. So you have increased the carbon chain by 1 carbon, and that 1 carbon, the methyl group, it came from your Gilman's reagent. So you can use Gilman's reagent to increase the carbon chain by reacting those Gilman's reagents with alkyl halides, preferably the primary alkyl halide, which is, in this case, it's shown the propyl bromide is a primary alkyl halide because the halide is attached to a carbon that is further connected with only 1 carbon or carbon chain. So the secondary carbons are the carbons that are connected with 2 carbons or 2 carbon chains. So if isopropyl bromide would be the secondary alkyl halide. The Gilman's reagents are not really very good with secondary or tertiary alkyl halides because the steric hindrance becomes too great for them to overcome in the transition state. So the activation energy is too great in case of secondary and tertiary alkyl halides. So in order to effectively use Gilman's reagent to get higher hydrocarbons, one needs to take primary alkyl halides. And that is also true for all substitution nucleophilic second order reactions. We will discuss those in some other video, but let's see now quickly. These are the reactions so far. We have seen these 3 reactions: direct addition by Grignard reagents. We saw the addition of Grignards twice, and the reaction with carbon dioxide. So these 3 reactions are the reactions that show the contrast between Grignard reagent and Gilman's reagent. Now, Are there any reactions that are similar? So what is the similarity between these two reagents? So there are the following two reactions. So first is the epoxide ring opening, and the second reaction is production of hydrocarbons when there is an acidic hydrogen present, or there is a proton donor, then you can synthesize the hydrocarbon. So let's have a look quickly on these two type of reactions that are similar. So epoxide ring opening occurs because the Grignard reagent is acting as a nucleophile here. So the first step is that the Grignard reagent nucleophile approaches the electrophilic carbon, less hindered electrophilic carbon of the epoxide, and you form the intermediate, which is again the tetrahedral oxide, and this in second step after acidic workup neutralizes to give you corresponding alcohol. In this case we have synthesized a tertiary alcohol, but depending on the starting epoxide used, the alcohol could be primary, secondary, or tertiary. Now the same reactions occur with the Gilman reagents as well. So the epoxide ring opening can happen with the Gilman's reagent, and similar steps. Here I have shown a different epoxide, but the general mechanism remains the same. So your nucleophilic ethyl group here approaches the less sterically hindered electrophilic carbon here. The epoxide opens, and here you form a secondary alcohol. As you can see here, the carbon chain has increased by 2 carbons because these 2 carbons are coming from the ethyl group of the Gilman's reagent. So these two reactions are where they behave in the same way. Now there is another reaction where both of these, in fact the organolithium compounds as well, would react with proton donors. So the reaction here we are seeing is, this is an acid. We know that alcohols are weakly acidic, so they would react, and Grignard reagents are also bases, and they are strong bases, so they would grab a proton and the corresponding hydrocarbon forms. Similar reaction occurs with the Gilman's reagent as well.